Good afternoon. I welcome you all for the final keynote of ICTer Conference 2017. The topic is Climate Data Analytics for Agriculture. Our keynote speaker is Professor Roger Stern. Professor Roger Stern is a professor of Applied Statistics at Statistical Services Centre in the University of Reading, United Kingdom. He obtained his MSc in Statistics from University of Sussex, England, and PhD in Statistics from the University of Reading. He worked as a lecturer in statistics at the same university and also have worked overseas for 10 years, particularly in Sri Lanka, Nigeria, and Niger, both in universities and in agricultural research institutes. His main areas of research have been on developing methods for processing historical climate data, particularly rainfall data, in ways that are of direct relevance to users. He is also particularly concerned with the development of effective methods for training in applied statistical methods in general and statistics in applied climatology in particular. His current role in the Statistical Services Centre is largely that of offering support to research activities in many fields, but particularly in agricultural research and issues concerning climate variability and climate change. He can provide expert opinion on data analytics, statistical applications, for example, planning of experiments, data organization analysis and reporting, statistical software, statistical climatology, analysis of historical climate data, training in research method support, and in statistical climatology. So I cordially invite you, sir, for the keynote.
Thank you very much, and thank you again to the organizers for inviting me to come down here. It's really been a wonderful week, and I think if I speak on behalf of all the invitees who've come from outside Sri Lanka, it's a welcome one normally assumes, and it's worked very well here. To actually on the plane find they had kiribat, and then to find when I arrive I can have string hoppers, and today I even had a kaju curry. This can't be beaten, so thank you all very much. So you may wonder at this title. I've changed the title from the one because I thought with the 50 years I would do something that was a bit more historical, and I will explain what still coming down from the mountains means as we go through. So what I'm going to talk about is an introduction, and then I'm going to try and come down from the mountains and tell you what life is like in the valley, and then have some ideas for continued change. So we're in the data revolution. Everybody must have heard of data science and big data. But before that, there was a statistical modeling revolution. Statistical models have changed a lot in the last 50 years. And we're on the 50th anniversary of computing, and a lot has happened in statistics at the same time. However, as I've traveled around the world, I've found quite a lot of statistics in many countries has largely been immune to these changes. So while the world has changed around them, quite a number of statistics lectures in many countries have carried on using the notes that were handed down to them a little bit from the 1960s. So many people are taught statistics. I often meet the statisticians of the future, and that's fine. But statistics is taught to people doing biology and medicine and agriculture and social sciences, and most of them, particularly as undergraduates, they hate it. They really don't like statistics. They like their own subject, but they don't like statistics. If they then become postgraduates, it doesn't change their mind about liking statistics, but they now realize it's needed. So all that's happened is it's changed from being an evil to being a necessary evil. And perhaps that's partly because part of their teaching is still at the top of the mountain. So I'm now going to tell you what it's like up in the mountains, and then I'm going to come down. I'm going to show you, you don't have to come down one way, there's other ways to come down. And then I want to talk about statistical software that sometimes is at the top of the mountain. So when I started, I was a student in the 1960s, and statistics was a very piecemeal subject. So I want to take you through a standard textbook in those days. There were usually 3 sections. There was descriptive methods, where you learnt about means and standard deviations, and maximum and minimum, and skewness and things like this. And then there was statistical modeling for small problems. And I liked that, because I learnt about a lot of distributions, and they were very interesting. I learnt about the normal distribution, obviously, but I also learnt about the binomial and the gamma and the exponential and the beta, and they were all very interesting. And I used them to solve small problems. Not very useful problems, because they were obviously artificial, but they were small problems. And then the last part of the book was more general statistical modeling. And I remember as a student thinking, where have all the distributions gone? Because that was regression and analysis of variance, and now my data had to be normal. And if it wasn't normal, you had to take square roots or take logs and add 1 and then hope it would still be normal. And I wondered why I was taught all about all those other distributions if you could never use them for real work. It seemed very odd. I was at the top of the mountain. Regression, I was taught, and that was different to analysis of variance. And covariance was confusing, because that was analysis of variance, which was with factors or categorical data, and then suddenly a variate came in. That was all very funny. And then chi-square tests sort of appeared. That's another, you see, the idea is at the top of the mountain there's lots of little streams. And I was learning about each of those little streams of statistics. And they were all separate, depending a little bit on your type of data. Depending on your type of data, you were another little stream. And it was all a separate course, and all very odd and confusing. And non-parametric tests were there. That's where you didn't assume any distribution. But they were only for small problems, and they still are only largely for small problems. There was no box plots, because box plots were only invented in the 70s. And that was an interesting guideline. When I go to many countries in Africa and I ask the postgraduate students, tell me about box plots, they say, what are box plots? In England, we have box plots in our primary schools. So that's another measure of whether the country has been moving on, at least into the 70s. As we came down, think of coming down, these little streams come together and form rivers. And that means that these different methods come together and they're more coherent. And that makes life simpler, both to teach and to receive. So factors and variates suddenly became part of linear models. Now factors are categorical data, and variates are number columns. Now we didn't have to worry. We could do our regression studies and our other analysis with a whole mixture of categorical and numerical data. Sometimes worries me that the econometricians seem still to take categorical columns and turn them into variates of 0-1s. In this day and age, when in the 70s we'd got beyond that. And this was now for a wide range of distributions. Suddenly the gamma and the beta and various other distributions could be treated just like the normal distribution. Aha, we were really coming down from the mountains. And this was only 1972. And log-linear models was what you could use instead of having chi-square tests for categorical data. And it did the same when you had the chi-square test was just for 2 variables. But log-linear models was for many. And it was now all part of a generalized regression analysis. I was very relieved in the 70s. I was starting to lecture then. In fact, I arrived here in 73, just a year after this had happened. This was a most exciting paper. And what was very interesting was there was interactive modeling to go with it. You could only use that, of course, if you had a computer. But GLIM stands for Generalized Linear Interactive Models. And this was taking a computer now and using a terminal and not doing the analysis, but doing just trying something out and then adjusting it, which you take for granted now if you do statistics. But it was a big deal then. The reason it was a big deal, I learned when I came here. And I've told a number of people, part of my job as the statistician here was to cycle from the university to the Department of Census with a pack of cards, a deck of cards on the back, and deliver it to their computer, and the next day to come back. And therefore you did your analysis in one go. Whereas now, it's much more comfortable to do the analysis, have a look at a little bit, and then turn it back. It worries me that not everybody's doing that. And if any of you have ever been confused by type 3 sums of squares from packages like SAS, that's because they started when statistics was at the top of the mountain. They're not important now, but people still have to worry about them because it's SAS, and SAS is an important statistics package. So, let me just come back. Now we could do regression in lots of different ways with lots of different distributions. That actually was a big jump down the mountain. But there was one thing it couldn't do. It could only deal with data at what I call one level. You had your equation, y equals a number of x's, which could be factors, categorical or variates, and some sort of residual. But you couldn't handle very well what many surveys had, which was data at multiple levels. If you'd done a survey at a household level, and then you'd interviewed the people as well, so you have two levels. You have the person level and the household level. It couldn't cope with that. It was only equations at a single level. Multi-level modeling was still a piecemeal subject. That was still at the top of the mountain. But people were working on it. And in the 80s and 90s, suddenly we had restricted maximum likelihood in GenStat, and these are mixed models in SAS. And then we found another nice thing, that the way people had attacked spatial data with Kriging and various things like this, which was again at the top of the mountain, now suddenly became part of these modeling. You see, the idea of multi-level data is that people in the same family are more closely related than people in different families, or people in the same village compared to people in different villages. They then found that that's what spatial data is all about. So this modeling now was a very good way of having a whole general formulation for spatial data. Whoa, we're moving down the mountain into the valley. And all these developments have continued. The analysis of extremes is now interesting, partly because of climate work. We really want, and the extremes distributions, you see, are not in the family that were coped for by the generalized linear models. So they've now been brought in. But that happened only this century, early this century. And then hierarchical generalized linear models have come in. This has continued. And of course, Bayesian modeling has now become extremely important, which wasn't important in the 60s. Now, you didn't just come down the mountain that way. When I was a student, I had a course on survey design and analysis. And that was very popular. And I had another one called the design of experiments. I don't know if you have courses on this. And this was the idea that either you design an experiment, it could be an industrial experiment where you set things at two different levels. So you either interfere and then see the results. Medical experiments are very often where you have some patients given a placebo and some patients given a new drug, and you want to see if the new drug is worthwhile. So that's an experiment, as opposed to having people taking different drugs and watching what happens. That's a survey. So if you interfere, it's an experiment, and if you just let them go, it's a survey, and watch. And so I had a course called the design of experiments. And I thought, that's interesting, I'm going to learn about design. But actually the course was on the analysis of experiments that somebody had designed. My course was mainly on numbers and analysis. I wonder if there's more to statistics than that. And those were separate courses. And that was all. So an experiment was separate to a survey. Aha, interesting. In the 1990s, I started working in an agricultural research institute. And that was the time when research went from things on research stations to doing research on farmers' fields. And it's been done very badly, because the agronomists knew all about experiments, and the economists knew all about surveys. So now the agronomists went to the economists and said, you're going to help us because we're going on farm. And they turned everything into economic exercise. See, one of the interesting things when you go on farm is that you can do an experiment on the farmer's field. You can put different treatments there. But you also would like to ask the farmer some questions. They didn't in the early days because they weren't doing that sort of thing. They did experiments. Now, these two subjects of surveys and experiments have come together. But not if you're still at the top of the mountain in your teaching. You still teach them separately. 1980s was also the beginning of the design analysis of participatory studies. Everybody said questionnaires. Who designs the questions? Answer, the researcher designs the questions. Who answers the questions? The respondents. So this is extracting information from the respondents about the agenda set by the researcher. Couldn't we have things where it was freer for the respondents? And this was participatory methods. And for a long time, this was separate from, thought to be separate from what statisticians do. And sadly, to my mind, many statisticians I've met agree with the social scientists that the design and analysis of participatory studies is not their domain. Of course it's their domain. You have to choose your subject, you have to collect your data in nice imaginative ways, you've got to analyze your data. That is statistics. And there's a nice book recently called Who Counts? It's a very nice title, think about it. Who counts? Does that mean the respondent actually counts? So it's got to be participatory, or it means that the participatory researchers are going to actually have to do some counting, which is statistics. It's a very interesting title of a book. I now want to move to statistical software, because to my mind, this is an extraordinary subject. So SAS began in 1966, SPSS in 1968, GenStat in 71, Minitab in 72. They're all popular packages now. In fact, these are the dominant packages now. Very interesting, because as we went down the mountains, these packages added new features for the research, but they kept all the old ones. If you ever wondered why teaching statistics with SPSS is confusing, it's because you've got everything from the top of the mountains, the middle of the mountains, and the bottom of the mountains. The same I mentioned before, type 1, 2, 3, 4 sums of squares, was when you were trying to do all your analyses at one go with SAS rather than having it interactive, which it is now, because SAS started in the previous era. But for the other computer people here, I have a quiz question, if you like, and that is, isn't it surprising when you think that computers only started in the 40s, that the dominant statistics packages now started 3/4 of the way back in the lifetime of computers? Most of the software I think you use, the languages you use, most of the tools you use, started after the 80s when we moved to microcomputers. Very interesting. So 1980s, the microcomputers, many new statistics packages. That included a little one by ourselves at Reading together with Colombo as part of our Reading-Colombo link. By the 1990s, the old packages had taken over again as the microcomputers were big enough. There were some new ones. Stata is an interesting new one. S Plus has now much less important because R has taken over. R is the free version of S Plus. And all except R require licenses, and most of these are annual licenses. Stata you buy. So now we have life in the valley, as long as the teaching's in the valley. Of course, new mountains emerge. Statistics keeps expanding. Statisticians aren't great at keeping up. There's bioinformatics, there's image analysis, there's machine learning, there's financial mathematics, participatory methods. It's actually a bit overwhelming for the statistician. It's the same thing for computer scientists if they try to keep a breath with a whole of computer science. But could they have eye-openers on these subjects so they understand some of the principles behind them, and just a little bit so they're not totally strange? I think courses now, or degree courses, should incorporate some eye-openers so that the statisticians have a breadth of knowledge and they can then contribute to discussions. And I want to move now to the broader picture. I'm first going to consider the broader picture with data. So in my work as a statistician, I work with scientists, whether these are social scientists or whether they call them scientists, researchers, if you like. And by the way, I'm not very keen on this supposed distinction between research and development. To me, a lot of development involves some discovery element, which means it's research. So there isn't a tremendous distinction. So I'll call them scientists here. There's certain things that involve data that the scientist does by itself, the stuff that needs to be done together, and the statisticians also have a role. So what are they? Well, this is what's typically done. The scientists get their data organized. They need to know the research questions. They need to understand the theory that could support models, and then they need to interpret the results. Otherwise, they can't write the papers. Meanwhile, what has the statistician been doing? Well, the traditional course means the statistician gets involved, whether it's big data or ordinary data, it's very much on the modeling and the data side, or it's on the calculate and display side. So this is where the statistician's working. But it doesn't work like that, if that's all the statistician does. The statistician isn't yet working with the scientist. There's a lot of other things they should do, both the statistician, and statisticians aren't taught much on the work they could do on the quality control, checking, the reshaping, the merging, what some people now call data wrangling. There's very little data wrangling taught to statisticians currently. So the statisticians should be having a much broader training and getting involved in a broader way. And I hope the training is holding up to this. So this is what happens typically in terms of statistics. Statistics has a lot on data analysis. And it's getting worse now, if you think it's worse, because this whole subject of data science is steering people towards data, which is good. But is it only data? And what about the other parts, which are rather small here? Don't we need to be teaching now statistics plus and thinking what the plus is? So here's what I would like to see statisticians learning about. And it's not just data, it's broader than data. We've called it data flow. And the various topics here that I think are not taught, where I think the statistician, as part of a research team, can have a very important role. What's happening now is that the traditional teaching of a statistician is very much, I'm trying to use this pointer now. Am I getting there? Yes. Is very much on the statistical analysis. It used to be on the modeling. Now there's much more descriptive, because there's the data science coming in. And the data science also means some of this data wrangling, which is data entry and organization. And maybe data collection, but a lot of data science is to do, if you think of surveys and experiments, as there's three sorts of data. One is a survey where you observe, another is where you interfere, and the third is where the data are just there. They weren't collected for your study, but you now think you can make use of them. And a lot of big data is like that, where you think there must be something in those data that would be really helping a wide range of problems, but it wasn't collected for that purpose. I want to talk about two more of these boxes, just to give you an idea of work that we've been involved in, which we've found is important. The first box is called data ownership. We found to our cost that if you have a team collecting data, unless right at the beginning you say who owns each set of data and when can they be shared with other people in the team, there is chaos. Similarly, if you don't initially sort out, at least tentatively, when you write some papers, who are the authors, you get in a mess. So let's discuss those right at the beginning. What are we aiming for? What papers might be written? And who owns the data? And what's going to happen to it? And hopefully, and if you're working in medicine, it has to happen now already, hopefully it's going to be archived in a way that's publicly available. If it's medicine, you're not allowed to publish a paper unless you supply the raw data. Other subjects are way behind. And another topic that's way behind, and we're doing a lot of work on now, is that if you do a survey of farmers, what do they get back of the results after the survey? Are they even told that the student got a PhD? Are they told anything? So can we have information flowing in different directions? And the fact that so many people have at least mobile phones makes this a totally different subject to a few years ago. I see these whole boxes as part of the statistician's repertoire, but I don't yet see it in very much of the teaching. There is change. Interesting report in 2016, the Gaze report in the States, was advocating quite a number of things. But I should mention that a lot of the things it advocates I've seen in Colombo University. So you've been duly, I hope, impressed by what's happening in computer science. in Colombo. And you've seen, I think, if you've been here in the last 2 days, that the history of computer science has been very entwined with the history of statistics at Colombo. What I've been very pleasantly impressed with is the quality, standard, and caliber of the statistics department here, as well as the Department of Computer Science. I don't want to take anything away from the wonderful achievements of computer science, but I think that statistics, by the standards of most of the departments that I meet, is very strong. They tell me and maybe the students or staff from other universities, they tell me they're very strong by Sri Lankan standards. I think they're much stronger than that. So I think there's a very interesting department. And when I discuss some of these, what I call more modern ideas, I find that they're already using them. So Gaze had this interesting report. New Zealand has some interesting work. It's very innovative in New Zealand. By the way, there are 50 MSc courses in the UK on data science. Whether that's a good thing, I'm not clear. I would prefer some of these courses to be integrated, so it's not just data science, but it's for something and with something. And Colombo, as you might expect, has a data science research group, so they're keeping up with it. I want to talk very briefly about 2 resources. Maybe if they're not being used, they can help. One of them is a book, or a series of books, called CAST, Computer Assisted Statistics Teaching. I wonder if that can help. This is from New Zealand, from Massey University, and we've been working with the main author for the last 15 years, and he started the books about 17 years ago. Very interesting set of books. I want to explain why I think it's interesting. One reason is the results. So we taught some courses, and if you're happy interpreting box plots, you will notice the boxes where CAST was used show higher results from this course. And what's much more impressive to me is most of the students, these were, by the way, management students who didn't like their statistics beforehand, and they did like their statistics when taught with CAST. And the average went from 55, which is the national average, to about 70. And by the way, the evaluation was not by the people teaching it, because this was a national exam. And so suddenly, this was in Western Kenya, the management students from Western Kenya suddenly were all outliers, and the national body wanted to know why. The answer was CAST. So what is CAST? Here it is. It's a whole set of statistics textbooks. However, most books are passive. This is pretty active. So it's highly interactive. And you all know that when you do something, you learn more than when you're just passive. This is an example where if you go on the left-hand side, the student moves the slider and a bar chart becomes a pie chart. So they begin to see not just that there are bar charts and pie charts, but what's the relationship between them. Answer, they move coordinate systems. Here's an example that in Africa people find rather difficult. So this is an example now of the testing system. Well, it's a set of exercises in CAST. So I'll read this question. I think I have time. I do have time. The photograph shows a crowd of football supporters at a match. The mean weight of the supporters is 80 kilograms. Guess their approximate standard deviation. Now, the interesting thing about these exercises, if you look down at the bottom, it says, check, tell me another question. These are, and I think you heard quite a lot about different forms of assessment this morning, these are mastery ideas, that you can have as many of these questions, and there's just different subjects, but the same idea, until you've really understood how to estimate a standard deviation in the real world. And if you think you've got an answer, you can press check. And it will try and tell you not yes, no, but if it's no, it will say, is it a bit big or a bit small compared with what it thought? Of course, you can't get the right answer here because you haven't got the numbers, but you can get an idea. Let me just give you an example which shows what can go wrong. A group of statistics MSc students who'd been taught theoretically I gave them the following example. Supposing you have some data which is roughly symmetrical and between 10 and 20. I first asked them, what roughly would the mean be? And it took a bit of prompting before they said 15. So it's between 10 and 20, the mean is 15. Roughly, how big would you expect the standard deviation should be? And they looked at me as if I was mad. How could they possibly be expected to answer that? I hadn't asked for a formula. I'd asked for a number, and surely I hadn't given enough data. So I said to them, let me give you a ridiculous answer. And they said, fine. And I said, I'm going to suppose the standard deviation is 100. What do you say? And there was silence. And I said, you should be saying, that's far too large. Okay, they said, it's far too large. Okay, I said, what's the standard deviation? And quick as a flash, this student said 66. Now, it had to be, the mean is 15. The extremes are 5 from the mean. The standard deviation is a typical deviation, so it's going to be 2 or 3-ish. That sort of number. That's what we're wanting here. The mean weight is 80. Probably they're between 40 and 120, so the standard deviation is going to be about 15 or 20. That's the sort of number. And it will say yes if it's reasonably sensible, because there isn't a single right answer. There isn't in the real world of many problems. So it's a book of exercises, but what's impressive on the exercises is, as I've said, you can keep practicing them. So the students who got better marks, they practiced different exercises on their topics. They then asked questions if they couldn't get it, and they could go back to the theory part. And then the test they had was partly the same sort of thing, but without the chance to choose another question or the tell me. So the testing system, which was in Moodle, was doing roughly the same, but without the chance to keep choosing things. And they could take the test multiple times so that they could get a reasonable mark, because each time they took it, they'd actually have a different question. So CAST also has the opportunity for the user, let's say me, because I'm giving a new course, to adapt the standard books to my own books. So we have, I think, quite a nice course called Statistics Made Simple, and I wanted a book to go with it. So I adapted the book, the standard books, and took the bits I wanted out and made my book. By the way, with the skills of the computer center here, that book could be in any language in principle. I just wonder if it could be in Sinhala. Because you've got total, they're all free, by the way. So I prepared the book, and there's my book. I had 10 chapters in the course, so I made 10 chapters in the book, one for each of the weeks of the course that goes along with it. And I put the, so these went along. We had what is statistics, describing data well, making good generalizations, testing hypotheses. These were each of the bits of work that we had in the course. This is the course. It's an e-learning course, which has an e-book with it. By the way, we sell the course, but we give away all the materials within the course. So if anybody wants the materials for the course, they're absolutely free. And if they want to use those materials to make their competing version of this course, they're very welcome to do so. And here's an example. And I want you to notice that when you use this book, have you seen in the top right-hand corner, it says brief, full, and video. So you can either have a summary of each page, or you can have the full thing, which is interactive. And if you slide that proportion along, you find that it goes to quarters, so that you can understand the box plot. Or if you're feeling lazy, you can have a video. There's about 600 videos which discuss all these different things. Hey, and that's all free. And if you don't like it, you can adapt it. If there's bits that jar and you think you want to change it, you can change it. The second item is our own little software. I told you before, and this is the last thing before I tell you my final conclusions, we have a project we're developing a little software called R Instat. We feel R is the future. We used to have a little package called Instat. So now the new Instat depends solely on R. And we think that maybe it could be useful for those people that cannot afford commercial packages, or they find R is great, but either R is too difficult, or they would like to have an easier route into R. And so we are developing this little software, and my dream would be that we've been developing it for 2 years. I brought copies with me and left them with various groups here, that maybe in the future we could renew our collaboration. The first version of Instat was developed jointly by Colombo and Reading. Maybe the second version could also be a joint initiative. That would be great fun. And this is what our Instat looks like. It's not looking like the traditional R. And we claim it's as easy to use as a spreadsheet. Looks like a spreadsheet. You see down at the bottom there's multiple sheets. You can right-click and get a little menu to do various things, and you have sensible graphs on the right-hand side. Oh, and by the way, you can have special menus, and we have a special menu to study corruption, which I think is interesting. So these are my conclusions now. I think in teaching statistics, if people have not totally come down, or they're not teaching a broad enough course, the directions for change are clear. Now, the feasibility of change is recent in some countries. It's not that recent in Sri Lanka because of Professor Samaranayake. Namely, you need to have some technology available before I think it's feasible to make quite a lot of these changes. But now the technology is available everywhere. And I think the change can be done. We have to accept that in many countries, people have large classes, they have heavy teaching loads, and senior staff who are relatively elderly may feel threatened by change. I don't think this matters. However, the counter side is change can be really fast. I think there's exciting things happening. Wait and wonder. Thank you. I occasionally find when I finish the talk, I am willing to answer questions, but I've totally silenced the audience. If you're not totally silenced and there are any questions, then I'm quite happy. Of course, if there aren't questions, we catch up a bit of time. That's a very nice question. We often enjoy teaching our statistics students, and we think that's relatively easy. And we think it's even easier to teach service courses in statistics to people who aren't going to be statisticians. And they're in many different disciplines. And often junior staff do that. My experience has been it's much harder to teach people who aren't convinced they want to do statistics. And as you've said, they're in many different areas. What we find is we have to do a little of a salesman's job. I've found in my career that part of the role that I can play is that when somebody comes along with a problem, then I may not know that area. The first thing I have to do is learn enough about that area to communicate. Otherwise, it doesn't work. The second, and once I can do that, and that may be by myself, or that may be that two of us teach a course together. Having done that, the skill that the statistician should have is that the principles behind the use of statistics are the same, almost whatever the area of application. And so I find that the main thing that I can add is that many people in a specific subject area learn about a few techniques. And I'm sometimes able to say, aha, that problem in your area has different words, but when you reduce it, it's the same as this different sounding problem in another area. Have you looked at this method? So I find that I have to fight a little against the people who will only think about an example where it fits exactly with their research area, and ask them to be a little patient. But then many of the problems is that people haven't been teaching the principles. If they teach the principles have to cut across these areas, otherwise it isn't statistics. If there's totally new principles, then it has a new name. So the thing we have to do better than we do is to really try and teach these principles in very simple ways.
I have a small question. Well, data analysis is a common problem, comes in many disciplines. Both quantitative analysis and qualitative analysis, what we see it, statistical methods are more, commonly used in the quantitative analysis. So how do you see the qualitative analysis? Because sometimes people, non-science people approaches, we consider scientific approach more to bias towards what I feel it for the quantitative analysis. And at the same time, I have seen in many studies, people mix them as mixed methods, both them, and trying to bring a better value for the conclusions. So in your opinion, how do you see that?
Another very good question. The question was that a lot of people see a big distinction between the analysis for what I'll call a quantitative study and a qualitative study, or a more qualitative study. What is the distinction? And what does one do? And you've concentrated on the analysis side. Before we get there, the design side, to me, becomes important. There are aspects of a qualitative study where the stats doesn't come in. Many qualitative studies are linked to empowerment and the participatory methods. And they're not trying to get a sample from a population and then generalize to learn these general methods. That's slightly different. But in many studies where qualitative data are collected, the analysis still has to proceed. I'll give you one example of a study which used more qualitative methods. This was in Malawi, where they gave a starter pack of seed and fertilizer, sort of legume seed, vegetable seed and fertilizer, and good maize seed to some farmers. And then after a few years, they gave them to the poorest half of the farmers in the village. And the question then was, who chose the poorest, and were they really poor? And people in rural Malawi are really poor by many standards, and so this wasn't a question of measuring poverty by how much money they earn, because they weren't earning money. And so the questions had to be rather delicately phrased to find out about this, and the data collection method used a number of qualitative methods. However, the results had to be generalized to the whole of Malawi. Were the poorest actually receiving the aid? And one example, which is quoted quite a lot, is that one definition of a poor family is a family where the children are, or the people living in the house are orphans. And an orphan, of course, is defined by not having your mother or father. So the chief of the village, who was in his 70s, said he didn't have his mother and father either, so he was an orphan. Now, he, by other standards, was pretty well off. And so there were instances like this which were extreme. The data collection now proceeded and was very statistical in the way the samples were chosen. The actual data was rather qualitative and came as a result of discussions and pictures and all sorts of things, and particularly lots of maps to be able to discuss things. And then the analysis, of course, you're absolutely right. These maps, if they're going to be analyzed, have to be interpreted and coded. And so there is an interpretation and a coding step which renders the results of a map into a number of numbers. And this was then analyzed. So I think there's a lot of analyses that can be done, but there's an extra important, the data wrangling step becomes quite difficult and quite varied. There's special software to help, but there's that extra step. But I would still think that statisticians have a big role to play. Okay.
So we really appreciate and would like to thank you, sir, for your coming and the interesting keynote. So I cordially invite our Dr. Nalin Ranasinghe to felicitate Professor Rogerson. Yes, sir, please come into the middle of the stage to hand out the plaque. Thank to both of you, sir. So it is the end of the keynote, and we have paper presentations after this keynote. The simulation and